All right, guys, let's get going on this. I'm Charles Nutter. I'm going to give you a little replay. Hello, everybody. I'm going to give you a little replay of the FFI talk I did yesterday. Talk a little bit about how we're making it easier to call native code on the JVM and what the future might be there. There's basics about me. Nothing too particularly interesting there. So I think about this in terms of sort of the bubble that we live in, this managed runtime that we wrap ourselves in like a warm blanket, and we never look outside of this. Wrap that towel around our head and live inside this Java world. But there's an entire other world of libraries and developers out there doing great things, but not necessarily on top of the JVM. We should be able to use these libraries very fluidly, very easily from our Java and JVM applications without having to write native code or leave that comfort zone of that managed runtime. So hopefully this FFI work that we're doing will help sort of punch a hole in that bubble of the JVM. So let's look at our world, the world we live in here on the JVM. We have this wonderful managed runtime that keeps memory safe and makes sure we don't walk off pointer edges. We've got all sorts of safeguards, keep us from segfaulting our applications, keep us from ever having actual null dereferences in native memory. Very good development debugging cycle and awesome tools for this platform. We have all this stuff that makes the platform very easy to build applications that are stable, fast, reliable. But the problem is that when we want to evolve this platform, like NIO2 in Java 7, adding new file system features and so on, we have to wait. We have to wait and beg Oracle and beg Red Hat and beg other folks that work on the OpenJDK level to implement these things. If we had access to just call these libraries, if we could call down to the C++ level or C level, down to operating system features, we could have had NIO 2 years ago. We could have had NIO years before it was ever added to the JVM. And we could have implemented it entirely in Java. So we need a better way to be able to enhance the platform using these native features. So here's our world, and we have a lot of wonderful things here. This is just the base platform. Of course, there's tens of thousands of Java libraries out there, but we kind of get this tunnel vision about what's available for building our applications. We only look at things that are on the JVM, and if it doesn't have a JVM version, it doesn't exist to us. And that's terrible because there's crypto libraries, graphics libraries, databases, a whole other world of libraries and utilities out there that could be accessible to us and could expand what we can do with our applications if we could call it. We've got all this stuff down at the bottom here. This is the stuff that's hidden from us, the stuff that we have to wait for the JVM engineers to expose for us, to allow us to have access to. File system features I mentioned, like NIO2, different types of network sockets, like being able to create Unix sockets or raw sockets for various applications. Actually having truly interactive sub-processes is almost impossible on the JVM right now. Process Builder gives you buffered streams that aren't selectable, and you can't actually use an interactive sub-process and make it actually feel like you're controlling it directly. I mentioned crypto libraries, databases, graphics, GPU stuff. Lots of things we could do if we could punch through that bottom level. And that's what we're trying to do with FFI now. A lot of this also came along because as I was working on JRuby and trying to provide a solid Ruby environment on the JVM, there were features that just weren't available to us. For example, the file system metadata, symlinks, and so on were not available till Java 7. You still can't do really nice sub-process stuff. You can't do stat to get lower-level file system information. Console controls, NoSQL database drivers that are based on C and don't have a Java equivalent. Replacing C extensions that people write for CRuby. All sorts of things that we needed to have in JRuby just to be able to say we were compatible, to say that we could run Ruby applications. And the only answer for us was to build an FFI and have our own way of calling down through those levels. Now, hopefully, we'll be able to bring this to the masses. So let's look at this the traditional way. How many folks have done any JNI development here? There's a couple, yeah. How many of you all really love doing it too, right? Oh, yeah, absolutely. It's so much fun. So let's look at what JNI actually looks like for folks not familiar with this. You've got some user code at the top, that's Java. You've got a JNI call, you mark a native endpoint. That's the Java stuff above that line. And then on the other side, you have to implement a little bit of C code to actually make the native call to some target library. Now the problem here is that this is kind of deceptively simple when you start looking at this. If you need to call a native function, okay, the first step, all I have to do is throw this keyword on here, native, right? Now I can make native calls. I can call getpid at the operating system level and get the current PID of the current process. But there's so much more hidden behind the scenes here. You have to generate all these header files and interpret what they mean with their long mangled names, which one actually maps up to the code you need. And so, okay, you can get past the header files, and it's all generated, so you don't have to write this. Well, you still have to write the C code that goes along with this. And of course, this is probably the most simple example of something that you might do in JNI. If you have to work with input arguments, passing parameters around, returning values back to Java, very, very complicated to do this at the JNI level, when all we want to do is make a simple call to a C function. And then even after you've got all that done, you've got to figure out how to compile this on all these different platforms. You need to have either a make file that people can use to build it on their systems, or you need to build binaries across all these platforms and ship it with your application. And so now we're completely breaking the idea of this managed world, this write once, run anywhere world, by hooking it up to these native things that we have to ship for every single platform. And that's not going to work out. It's just too much overhead, and it slows down both application development and the enhancement of the JVM itself. So this is a quote from John Rose, one of the core JVM folks. I think he's the JVM architect lead now. If non-Java programmers find some library useful and easy to access, it should be similarly accessible to Java programmers. I mean, who would argue with that? There's great libraries out there, great tools that we don't have access to right now, and we should. So let's fix that. So what we need a Java API for binding native libraries and managing native memory so that we never have to write C code again. All we do is tell the JVM that we want to call some native function with some native memory structure, and then it will do it for us. It'll handle all of that for us with no C code. And that's where we have the Java native runtime. Java native runtime, the JNR organization on GitHub if you want to check it out. This is a Java API for calling native code, supported by a rich set of runtime libraries and utilities that we've built around the core. Some of you may be familiar with JNA, the Java Native Access Library. It's very similar to JNA, but we've made a lot of enhancements and improved performance significantly over JNA. And I'll talk about the performance stuff a little bit later. So looking back at our JNI example here, this is what you typically have. And you end up writing basically everything up until the target library, including that C code. We don't want to have to do that. When you use JNR, all you end up having to write is your user code at the top with a little bit of Java interface definition to tell JNR what C function you want to call, what library it's going to be in, what the arguments look like. The rest of it from there down is provided by JNR. It allows you to call any native function, marshals values back and forth, helps you manage that memory directly, and you never have to write a line of C code. And now, how can you do that? Compared to the JNI, this we define our interface, getPid. We define the function, getPid. We're not interested in the error return value resulting from this, because typically getPid will return no error. It'll just return the current PID. Down in the main there, we create a new library loader for this interface. We tell it what library to look for that function, or look for this interface's functions in this case, libc, and that's it. Now we actually are making a down call directly through libc into the native function getPid without having to write a line of C code and without having to ship anything special per platform. It's like magic, right? Well, let's look at how we're actually doing this. We'll go through all the various layers of this and kind of explain how we've built this whole runtime library, this whole for doing native interop on the JVM. First of all, libFFI is the actual native C library that we use to bind these functions. It knows how to load up a shared library, look at all the symbols that are exposed to it, and then do some of the basic marshalling and invocation of those functions. So nothing that you'd see here at the JNR level, but it kind of starts with the base right there. Above libFFI, we have Jffi. Jffi wraps it with just the thinnest possible JNI layer for doing various types of invocation, different widths of argument lists, different types of call protocols, and so on. The basic things just to call across that boundary. Again, not something that you would generally use unless you want to build your own FFI layer on top of this for another language like Groovy, for example. JFFI is, however, where we actually ship the native binaries. And these are the platforms that we support currently. If you put the JNR artifacts in your Maven builds, or whatever you're using, Gradle or whatever, you will get all of these binaries for free. We've built for all these platforms. If there's any platform that's not on here, it's not that difficult for us to get another binary in here. The builds usually don't have to be redone very often. As I said, the JFFI layer is very simple. So anybody doing anything on a platform that's not listed here? I thought somebody might have mentioned ARM64, which is not on there, but compiling for ARM64 again is not going to be a big problem. A couple not listed on here. There's the AS400 build is actually working now. I don't think it's committed to the repository, and I think the OpenVMS guys have their build as well. So for all you OpenVMS users doing a lot of Java applications, we'll be able to support FFI there too. But this is the general idea. A small stub that we can ship for multiple platforms doesn't require a lot of maintenance on the JNR side, makes it possible for you to do native calls on any platform without writing any native code. So let's move up from there to a more interesting user-level API. JNR FFI is what you would actually be calling. That's what you saw in the example earlier. That was the JNR FFI level of JNR. Roughly equivalent to what you get out of JNA. Define your functions, say where to find them, say how the arguments and return values map, and then you make the call. There's also support for making structured memory layouts. Say if you want to do a file stat at the file system level, say where all the arguments are, what the bit widths or byte widths are of all these arguments, and then JNR will handle mapping that across and proxying to the native structure and the native memory. Callbacks is another one that we added with the JNR. Actually can pass a C interface, an implementation in Java of an interface out to C code as a callback, as a function pointer. And then the C code will be able to call back up into the Java library, again, without having to write any C code. It just magically handles, giving it a magic pointer that calls back up into the JVM. So now, why didn't we use JNA? I mentioned the performance a little bit. The other problems was that JNA wasn't really low level enough for us to build other APIs, like the Ruby FFI that we have in JRuby. It didn't have any support for generating or gathering preprocessor constants. If you're going to create a native socket at the native level in the C library, you need to have access to the constants that say, is it INET 6? Is it an INET 4? Is it a Unix socket? Those different types have to be bound somewhere into the library so that we can call the native code correctly. And as I mentioned, C callbacks at the time were not supported. They may be now, but it's something we had to add to JNR. And we certainly did a lot of work on performance too. So let's talk about some of the support libraries, moving up from JNR FFI. So JNR constants is where we actually have our preprocessor constant library. There's a couple pieces of code to generate basically Java enums for different platforms to represent those native constants. So for the different socket types, 4 different file system attributes, and so on. Most of these are already pre-generated. We've got a large number we ship. For example, the file control APIs at the C level. Here are socket types and socket options. Protocol families for what sort of protocols you plan to use on over a native socket. TCP flags, sysconf. There's a number more, there's many more than this. Signal handling, being able to actually do proper process level signal handling without using a sun misc secret class all the time. We can do that very easily with this. So this basically just provides all of those static constants that would be handled at the C compiler level so that they work across platforms and you can use them from Java. There's an example of the socket types. Stream, datagram, raw, RDM, which is another type of dgram, and sequence packet, which I think is an OS 10 or a Linux only one. But again, just an enum, and this is just the Linux version. What we give you in the library is you would go to jnr.constants.sock, use the right name, and it maps it to the right platform value wherever it actually is. An example of how we're using this in a Unix socket here. We're calling down to the socket function. This is just the native C socket function, telling it we want a Unix socket that's a stream socket, and then giving it some information about what types of selection operations we want to do on it. And that's all there is to it. Using these two libraries together, we can call any C function and give it the right input and output values. All right, so another side library, a library for more convenience to help folks get into this stuff, JNR posix. It's a pre-bound set of the posix functions that we've needed on JRuby. Things like symlink access, execs, sub-process launches, so low-level file system operations. All of these things bound already for you and tested and working in production with JRuby on lots of platforms. The Jython guys have also worked with us on this too, kind of sharing this library, hoping to eventually have all of the POSIX functions you would ever want to call, potentially 100% of them, bound and ready for you. So all you have to do is pull this library in, and you basically have libc on the JVM at your fingertips. This is a small subset of what we have. Being able to actually chmod, chown, change the ownership flags of files at the file system level. Exec if you want to actually do a full process replace. Fork is bound and really crashes hard when you call it, so it's a lot of fun to see that dump. The JVM does not fork well, I'll tell you that. But it's there for platforms where it might work. For example, Dalvik is a forkable VM, so that's a possibility that we could use fork there. Here's our Getpid already bound for you, so you don't even need to write any code for it. Password entries on Unix systems. What else? Symlinks, process priorities, thread priorities. Down here, POSIX spawn, one of the nicest ways of doing sub-process spawning and management. All this stuff available pre-bound. All you have to do is throw JNR POSIX into a dependency, and you can call any one of these very easily. So moving off to the side from that a bit, I talked about how you can create your own native raw sockets. You can call out to the file system, or to call it to libc and create your own open files, descriptors, and so on. But ideally, if we're working with file descriptors, we'd like them to work like NIO channels, right? We'd like to be able to pass them around and have the JVM treat them like any other stream. And that's what JNR ENXIO gives you. This extended native cross-platform I/O. And essentially, it's just an NIO channel with full interruptibility, selection capabilities that you just pass a file descriptor, and there you go. This is the basic interface that we have for it. Native socket channel, pass it some file descriptor, and you've got a full-on NIO channel for a socket type the JVM doesn't even support, like a native, or a raw socket, or a ICMP, for example. Example of using this in JRuby here. We wanted to have more interactive standard I/O. And so what we actually did is just take standard in, out, and air, wrap them in a native device channel from ENXIO, and now we get full selection capabilities, full console control capabilities that the rest of the Java world can only dream about, because the Java does console access so badly right now. We can just route around that with this API and have real access to real file descriptors without losing all of what NIO gives us. Very cool stuff. An example of something that we've actually built to sort of exercise this API, JNR Unix socket builds on top of ENXIO and provides a library you can call and create Unix sockets, Unix server and client sockets on the JVM without writing any code at all, any native code at all for yourself. Fully selectable again, pull in JNR Unix socket from in your dependencies, and you've got Unix socket capabilities on the JVM. There's the example. So we've got some file path where we want to have our Unix socket. We create our Unix socket address, very similar to how you would create a socket address for one of the standard JVM types. Create a server socket channel and open it up, and then tell it to bind to that address. Now we have a Unix server socket. We can use a similar process to create a client and get all the benefits of using Unix sockets. Faster communications, more secure, and so on. Okay, so I mentioned performance was one of the big reasons that we didn't end up using JNA. JNR is a complete rewrite, a completely new library designed for performance and for these tighter integration scenarios. So we're working really hard at making sure that JNR performance is solid, very good. We've got generated bytecode stubs to make it at least only one hop from your call down to the native level. In JRuby, if you're using the Ruby FFI library, we use invoke dynamic to even make that a shorter path, make it really just directly from the call site to some native code. On the native side, we generate at runtime little JNI stubs so that you can call from the JVM to the native function is just one hop. Not an extra C call in there, not extra JNI overhead if we can get rid of it. And in the best case, we're talking maybe 2 or 3 hops from a Java function call to a C call. That's pretty good. That's about as good as we can get it without routing completely around JNI. A side note here, one of the libraries that we're using to do this, another sub-project in JNR, JNR x86 Assembly. It's basically an API or DSL for generating x86 or x86-64 assembly, loading it back into process, and calling it through JNR as any other function on the system. How about that? So you want native performance. If you really want to write a Java application that's as fast as assembly, here you go. You can just write assembly. I don't recommend that this is something a lot of you are going to go out and do, but it's cool to note that this is here and how much it's helping JNR speed up that native call. So looking at the performance a little bit compared to JNA, it's not really a fair comparison. We are talking like about an order of magnitude faster. So if you've ever used JNA to try and do native integration and found it too slow, JNR is a great one to revisit. We're basically getting down to the point where it's just as fast as if you wrote raw JNI stuff yourself. Look at this, another aspect of this, you saw that there was the ignore error annotation I had on the Getpid before. If you don't include that, we will actually track the error number, the error value at the C level on a per thread basis. So multiple threads can be calling C functions. Maybe some of them have error numbers. It's all saved off for you. It adds a bit of overhead, but this is one way. If you know you're uninterested in the error, add that ignore. You can drop it down another 25%. And then compare to some of the other big contenders here. So here's JNR Getpid, just the standard binding, saving off the error every time. Oddly enough, we actually run this particular benchmark, which is just calling Getpid many times, faster than the JNI implementation. And the reasons for this are unclear to me, but my understanding from talking to Wayne, the guy who did our JNR native backend, is that the assembly code that we're generating is actually just a little bit cleaner and a little bit lighter weight than what you get out of hand implementing your JNI in C code. He can just skip a lot of the overhead, a lot of the extra stack manipulation and so on by doing an assembly stub that goes straight down to native. And now this is good. This is as good or better than writing this in JNI. But obviously there's more work to do down here. We're not competitive yet with writing the same thing in just a straight up C library or C application. So what are we going to do? We got to fix this problem and improve it even more. The problem here is that here's the assembly code we get. Everyone knows assembly, right? This is the assembly code that we get for the call from Java code down to Getpid. And down here at the bottom, what it ends up eventually doing, we've got our invoke interface Getpid. That's the Getpid interface function we created. And then it goes into the mechanisms underneath JNR. It calls through JNI, and we don't really get to see anything beyond that point. That's all generated code or native side. We don't get to actually see the Getpid call. Now, what we'd actually like this final line to look like here is this. What we want is that the JVM will recognize that we're doing a native C call to a particular library and bind that library directly in at the assembly level. Skip all the JNI overhead, and then we actually can do native calls without writing any C code just as fast as if you wrote them in C and compiled it at the command line. So that's what the goal is now. So we need JVM help to be able to do this. We want to see a standard FFI API that's part of Java, that's built into the JDK. We want the JIT, the hotspot compiler, to actually understand what it means to do a native down call from Java to one of these C functions and be able to get rid of some of that overhead for us when it's obvious that we don't need it. And we also want it to bind that native call directly at the call site. If you're calling Getpid in a piece of code, when it compiles down to native, that call should be Getpid in the native code as well. We shouldn't have the extra overhead there, especially for something that's very cheap and unlikely to cause problems for the VM. Should be able to do a straight C call to it. So where are we on that? Well, the first step for this was making noise last year. I finally decided that we needed to talk about this at the JVM level. So with the JVM Language Summit, I presented a similar talk, expected to be basically booed off the stage. I'm coming into a Java conference, a JVM conference, talking about how desperately I want to call C, right? Luckily, The presenter immediately before me also talked about this, so I think everyone was kind of tired and just sort of gave up at that point. So it was fine. Everybody actually got really excited about this. And what surprised me most was that the core OpenJDK folks were some of the most excited because they hate writing JNI more than anyone. And they've got all of that code to maintain in OpenJDK that we can sweep away if we can get this done. So everybody's really excited. This is going to happen. We're going forward with it. Step 2 was to have a JEP, JDK Enhancement Proposal. So JEP 191 I proposed for foreign function interface, a standard one on the JVM. That has now been accepted as a JEP, and we actually have an OpenJDK project that is in progress to start adding this to OpenJDK for future release. Project Panama is that OpenJDK project. It is a full-on OpenJDK sub-project. You can go to OpenJDK and find it there, look at the repository, and see the work that we're doing on it. Initially, just looking at having internal APIs so that at the JDK level, we can start sweeping away some of that JNI code, make it easier to evolve the platform, tie into native level features, hopefully looking that we can do a JSR in the future. That will be kind of a to-be-done sort of problem. We need the JEP underway. Right now, we're just getting the code in there. It just got approved a few months ago. We got a repository. Once we get the JEP working, compiled, building, all functional, then we'll see if we have time for a Java 9 JSR, but we will start one. At the very least, we will get the JSR going. Depending on how fast things go, small chance it could make 9, but maybe might be a Java 10 feature. At the very least, you can check out JNR. Hopefully, we'll be able to have JNR leverage some of those JVM features as they come along, and it's already pretty awesome too. So how can folks like you help? Well, if you are doing any native interop or you need some library that you need to call, let us know. Let us know whether JNI works for you, what doesn't work, whether the performance is where you need it to be. We want to just try and improve things in the open source project, the JNR organization, get this library as solid as possible, because mostly it's going to get imported directly into OpenJDK. So whatever you do to help us improve JNR is directly going to lead into Java 9 and Java 10 support for native function calls. And definitely tell everybody that you know that needs to do a native interop. A lot of folks don't even know about JNA, much less JNR. So we need to get the word out about this stuff. Let people know that all the cool stuff that the Node guys and Golang guys are doing with all these cool native libraries, we can do it just as well. We've got the access to this stuff now. All right. So that's all I have on this. Got some time to take questions, I think. Yeah, looks good. We've got a few minutes for questions. All right, thanks. Anything? Hey, all right. Right. So the question was, I talked about being able to possibly bypass some of the JNI overhead, the JNI safeguards, essentially. But how does that work if we're doing more complex types, passing Java values around, trying to get more complex structures back? Well, as it is in the API right now, anything that isn't just a primitive numeric value, primitive, under 64-bit width, would get marshaled back and forth in some way. Either you would hold a handle to native memory and your proxy your calls into it across that boundary, or you have a copy of it that runs on the JVM and then it's just a regular Java object. The potential that we could do with JNI, if we can see that we have an object in hand that represents a native structure, and we've got the function available, and we know this isn't going to be a blocking function, this isn't going to do memory allocations that the JVM wouldn't like, we don't need to do the extra safe points. We don't need the extra guards in those cases. Well, it's still kind of an open question how we would show that. There may be that at an expert level you'd say, this particular native call, I know it's non-blocking. I know it's safe to remove some of these safe points. Obviously, anytime we're going to be calling down to native code, this is getting to be more of an expert level or at your own risk sort of feature. But it should be possible to say, I don't need the JNI overhead here because it's a simple call. So we're looking at how that's going to be, and the JVM will be able to do some guessing for us. I'm sure there will be user hinting as well. Other questions about this? All right, great. Stick around. We've given away a Raspberry Pi in a bit, so Oh, I'm going to do it, actually. Hey, wow, all right.